Hello, hello. So yeah, my name is Jared. So up until about 2019, I spent most of my career doing like Unix, Linux stuff, and lots of network admin and network design. So mostly data center and enterprisey flavored stuff. In 2019, then I joined 151 Research, which was a small company started by Paul Card, to do some esoteric stuff in an attempt to get myself out of my comfort zone. Since then, the startup 151 Research was acquired by GSI AgCo, sort of a global big ag. But yeah, to say the least, I've been out of my comfort zone for a couple of years, which is good. I've been working on some cool stuff with some very talented electrical and mechanical designers, developers, lots of scientists, and some savvy business folks, I guess. And we're working on grain monitoring technologies. So this will be kind of a very different flavored talk for this conference, probably. I'm going to talk a little bit about grain storage and why, and then I'm going to talk about some of the communications technologies that we use to ultimately get data into customer eyeballs so that we can make good decisions for grain storage. I do need to preface the talk by saying I apologize for the non-metric units because we work with America. So if you're triggered, I'm sorry. Because I'm triggered all the time. So we're going to talk a little bit about grain storage. That's a grain bin. Those are grain bins. They're huge cylindrical steel structures, and we use them both for the short and long-term storage of grain. They have a conical roof, and we load them from the top with augers or drag conveyors, and we empty them from the bottom. This is a collection of kind of small bins, actually, near Dugald, Manitoba, one of our alpha sites. These are little, they're only about 35 feet to the eave, so to the lower part of the roof. But bins can be as large as like 100 feet tall, 150 feet in diameter, so like absolutely massive things. So the anatomy. The outside walls are corrugated steel sheets, which are bolted together into cylindrical, what we call rings, and the whole thing is just on a giant concrete pad. The floor, importantly, like this is a picture of a grain bin that's in the process of being built. The floor is raised above the foundation on risers, and those risers support a perforated steel floor. The space beneath the floor we call the plenum, and that allows air to be forcefully blown up through the floor, through the grain, and it exits out the roof. We have massive fans generally on grain bins, which can blow the air in. A lot of the times those fans actually have heaters as well. So why do we monitor grain? This picture is my colleague Pat. We're hanging a cable, one of many that's going to be inside this bin. So grains can the grain bins rather, can hold a massive amount of a commodity. And when I say they can hold a lot, if you just talk a dollar value, the larger commercial bins at inland terminals can hold like millions and millions of dollars worth of stuff. So obviously we want to preserve the value of the stuff as best we can. We're principally trying to guard against spoilage by rot and insect infestation. And we also want our grain at a temperature and moisture level that's sort of optimal both for storage and subsequent sale. So yeah, why do we care about the temp and humidity and also the CO2 levels in the bin? Well, so CO2 levels are interesting because it's sort of a leading indicator. Before stuff starts to really spoil or before the insects get really bad, CO2 will start to go up in that bin. And if active spoilage is occurring, then the temperature will go up within the sort of the mass of grain, the pocket of grain where it starts to spoil. So we can, by detecting temperature, we can detect grain rot as well as insect activity, which is kind of cool. Sorry, my speaker notes are kind of screwy here, so you'll have to bear with me. So we suspend these temperature and or humidity cables from the roof. We fill these bins from the roof, and these cables have sensor nodes, usually every kind of 4 feet-ish, along the length of the cable. And then the cable leads exit the roof. So a small bin might have like 2 or 3 cables. Large bins might have dozens of cables, so that means hundreds of sensors that are hanging within the grain. And again, they usually measure, the newer ones will measure moisture and temperature. So the idea of using cables to measure grain temp it's been around for quite a while. This is a couple of pictures of an analog system. We'll call it a legacy system. They use thermocouples, which are an analog device. So a thermocouple requires 2 leads per sensor, and they're arranged in such a way that there's a common lead down the cable, then each individual thermocouple has an additional cable, which leads to these like crazy complex wiring schemes, and which also leads to some, they're more prone to failures, and to read these things, like a human being has to come up to that plug panel and like put a device in and be like, okay, cable 1, what are the readings? Cable 2. So it's not ideal, but that's still much better than not knowing what's going on in the bin at all. Again, millions of dollars of grain is often in these things. This is a system in a grain co-op in the US. Again, they look old and nasty, but like this system has probably saved millions of dollars in its lifetime. So there's a very big retrofit market to say, like, can we plug smart stuff into these old cables and get the data into the cloud? Modern cable systems, however, are digital. In this case, there we go. We almost always measure temperature and humidity just because it's easier. These cables only have 2 leads, which are structural steel ropes down the length of the cable, and it's mostly using the one-wire protocol, so that those 2 structural steel cables supply both data and power to the nodes along the length. In this cable example, the green bit sits above the roof, and the blue bit hangs down into the bin. And again, they're filled through the top, so the cables get sort of like submerged in the grain. And yeah, they're kind of cool. They have a gas permeable membrane on them too, so that they can measure humidity. So they're kind of a cool thing. So let's talk a little bit about grain conditioning. I'm not a farmer, so this is sort of, there's a lot more nuance here, but so grain can come off the field either too wet or too dry. It's normally too wet for storage or sale. So especially in this part of the world, farmers will often put the grain through like a natural gas or a propane dryer before going into the bin. But a lot of drying can actually occur through natural aeration, meaning the grain's put into a bin and then outside air is then forced through the grain. So these massive fans, sometimes with heaters, will force that air up through the plenum, through the grain, and out through the roof vents. Drying the grain to a specific moisture level is not only a spoilage prevention mechanism, but it's also a big cost consideration. When grain is sold, it's sold by weight and not volume. So I guess the trick here is that the grain should be dried to the maximum moisture level that the grain elevator will take. And if it's too dry, then you're just like throwing away money essentially. So it's, precision here is important, and trying to be precise with 100,000 bushels of anything is difficult. So, and the fans are also important if we need to cool up the grain or cool down the grain. So, on a warm spring day after you have a bin full of frozen stuff, you can have condensation problems. So it's often important to have to raise the temp of the grain up so that you don't have massive condensation on the walls and the roof. So, but you also don't want to run the fans if the air outside is too moist. So you don't want to make your grain, wetter than it needs to be. So okay, this kind of a marketing slide, I guess. Whatever. My employer, we have a thing called GrainView. Marketing says that it monitors temperature, moisture, and inventory. It's cool. So inventory, so like how much stuff's in your bin. That's actually like, instead of having to climb the damn thing, you can just look on your phone. It automates the operation of the fans, again, for cooling, warming, rehydrating, whatever. And then you can get alerts if spoilage is sort of on the way. The components, it's not too big of a deal, but on the left-hand side, there's a little yellow brick of cheese. That's called our cable hub. That's the thing that actually actively reads the cables. It's kind of the heart of the system, honestly. Not shown, we have CO2 sensors, which live in the headspace, so that's the on top of the grain between the roof and the grain. So that stuff lives on the roof, and on the ground level we have the louvered weather station. We have a fan control module, so we have relays and contactors that can interface with the things that start and stop fans and heaters. And then we have also a gateway on the right that I'm going to talk a lot about, which is a communications thingy that's sort of my bailiwick. There's a whole slew of communication protocols that are spoken between these, but it's interesting or notable that the stuff on the ground talks to the stuff on the bin roof through RS-485, which is a common industrial, it's a serial protocol, whatever, and we deliver the power onto the stuff on the roof over the same RS-485 lines. Okay, so this is sort of my stuff. The communication system it's a lot of different protocols, so let's walk through it. On the left, we have our temperature and relative humidity cables. That's a one-wire protocol. We also talk Modbus over RS-485 to our CO2 sensors. And then we talk just plain old RS-485 with sort of like an in-house built comms protocol for reasons I don't understand to the fan control module on the ground. So then our cable hubs talk to the gateway through the LoRa protocol. We're going to talk at length about LoRa. The gateways talk to the outside world over 3G or LTE or whatever sort of crap cell signal they can get out of in the middle of nowhere. One thing that's notable is that we use what's called, I guess, an MVNO or a mobile virtual network operator. So instead of us having to get SIM cards for every provider in the world, we use one provider and we can drop these things almost anywhere. So let's talk about the LoRa thing, because I think it's pretty cool. There's LoRa and there's LoRaWAN. I don't want to confuse these two. LoRa is the physical signaling, the stuff on the air. LoRaWAN is a layer on top of that. It's a media access control and network layer on top of the LoRa physical signaling. Where does LoRa live in sort of the protocol stack? In this diagram, it's sort of the usual suspects. On the left-hand side, we have the sort of low-distance stuff, small-distance stuff, like the Wi-Fi's and the Bluetooths and all that crap. Top right, where we have longer distances and higher bandwidths, the 3GPP, the LTEs, et cetera, et cetera. On the lower right, we have the LPWAN stuff, which is where we live. It's low-power, wide-area network. LoRa, Sigfox, LTE Cat-M, and NB-IoT are kind of the really common things there. Out of all those options, LoRa is the one we chose because that's one where we can sort of build our own network. All the other ones, Sigfox and all the 3GPP protocols, require us to use someone else's network. You're probably being like, well, why not Zigbee? I use that at home, all the home automation stuff. It's easy. It uses Zigbee. It does, mesh network and stuff. We're in a really weird environment from a radio frequency perspective. We have bins that reflect signals everywhere. We have stuff moves around remarkably often on a farm. We have trucks coming in and out. We have buildings that get built. So most protocols, especially at the higher frequencies, just aren't appropriate for this. So LoRa is just sort of, when everything is said and done, it's the one that kind of works the best for us. So a bit about the LoRa PHY, or the physical signaling. The radio spec, I guess, is proprietary to Semtech. Some people are uncomfortable with that, but that's life. We use, I know everyone's like, open source, yay, and I agree, but whatever. In North America, we use the 915 megahertz spectrum, so that's an ISM band, unlicensed, if you will. So there are other users of the band. We use that in North America and Australia. In Europe, we use 868 megahertz, and there are additional LoRa implementations in the 433 megahertz bands. Most notably, there's a pretty cool satellite implementation. And there's also an implementation in the 2.4 gigahertz band where Wi-Fi and Zigbee and Bluetooth live. Transmit power is configurable and adaptive. And one of the really cool things about LoRa is that we have kind of banana pants link budgets. So what is a link budget? It is essentially the net power gains and losses that are end-to-end in a transmission system. So that goes from your transmitters to your cables, connectors, antenna, free space loss, and then all that other crap on the other side as well. So that's sort of the end-to-end budget measured in decibels. So a real-world link budget of 130 decibels is crazy. And LoRa also gives us the added advantage that we can often decode payloads below the noise floor. So we'll often have signals coming in where the signal to noise ratio is a negative value, which kind of hurts my brain, but it's, it smells like magic. So LoRa is a chirp spread spectrum encoding. So it uses chirps, and this is what it looks like in sort of the frequency domain. There's up chirps and down chirps, and that's how you encode your signals. It's pretty cool. We use either a bandwidth of 125 or 500 kilohertz. I think Europe can also use 250. One of the neat things about LoRa is you can vary what's called its spreading factor. So a spreading factor is the amount of time it takes to sweep up or down in a chirp. The lower the spreading factor, the higher the data rate, but the worse the receiver sensitivity. And conversely, the higher spreading factor, the lower data rate you get, but the receiver sensitivity is higher. Some cool characteristics of chirp spread spectrum are there's very good co-channel interference immunity. It's resistant to narrow and broadband disturbances, so it means it can really coexist with other protocols in the same frequency. And because they are just so darn different, that you can decode LoRa even if you have a whole bunch of other digital noise on that channel. It's resistant to multipath fading, which is super handy because, again, there's shiny grain bins everywhere that like to reflect RF, so multipath fading resistance is a really important attribute. And like I said before, it works really well in noisy RF environments, both from just like fan noise and variable speed drives, as well as other digital communication systems. LoRa spreading factor, again, it controls the rate of data transmission. So lower spreading factor means we have faster chirps and therefore a higher data transmission rate. And the lower the spreading factor, the longer range we kind of get. So I'm going to skip ahead. Why did I put that in there? Cool. So the spreading factor influences the data rate, both in bits per second, but it also influences our maximum payload size. So at our most pessimistic data rate, our payload's only 11 bytes. Like, we're not moving a lot of data around, but 11 bytes isn't a lot. And at our best spreading factor, we can move, I think, 250 bytes. So, think about that when you have to do an over-the-air firmware upgrade, which we can do, by the way. It can take a couple of days. Spreading factor also influences the distance and the time on air. So time on air is important because these are battery-powered devices sometimes, right? So if you're not on air, you're not draining battery. So a practical example of a time on air. So time on air, we're generally restricted by whatever regulatory framework we're living in. So in North America, in this band, we have what's called a dwell time, or a maximum amount of time we can hang out on one channel to 400 milliseconds. Sounds like a long time, actually, but it's in our best interest to use as small or as little airtime as possible, again, so that we can minimize our battery consumption. Okay, so LoRaWAN, this is the stuff on top of the LoRaFi. Did I change slides? One sec. Okay, cool. So this is the LoRaWAN architecture. From left to right, we have a device that's generally a battery-powered thingy out in the real world. We have a gateway, which talks the LoRaFi to the device, and then talks TCP/IP over some other transport. We have the join server, which handles the whole join flow, which is essentially sort of like a credential server, if you will. We have the network server, which is quite important. It does radio frequency channel coordination. It'll schedule downlinks, adjusts transmission power, and also it has a large part in the key exchange. And then we have the application server that does, application stuff. I don't really pay attention to the application too much. I'm the network guy. Okay, briefly, this is not a cryptography talk, but I just want to talk briefly about the join process. Um, Before a LoRaWAN device can interact with a network, it needs to join the network. This process happens generally when a device powers up, or if it needs to reestablish its session keys or reestablish its presence on the network. Once joined, that device can keep using those session keys until it needs to renegotiate for some reason. So maybe the device loses its mind, or it needs new session keys, or needs to go to sleep for some reason. There are two ways a device can join a network. One we call application by personalization, where we just use static keys and call it a day. That obviously is sort of like a toy protocol. We use that in the lab. We use what's called over-the-air activation in the real world. So that's essentially the device wakes up and it involves dynamic key derivation based on pre-provisioned keys. So that process briefly looks like this. The end device wakes up and sends a join request containing like the device's unique EUI and a nonce and some other stuff. The network server then derives two keys, the network session key and the application session key. The network server then sends back a join accept message to the end device, and then the network server distributes those keys to the application server and hangs on to one for itself. At which point, the end device does the same key derivation process, so it has the network session key and the application session key. The key takeaway here is that there's really two session keys here. One where the device can talk to the network server and get network instructions about what channels can I use, bunch of crap like that. And then there's the application session key, which encrypts the application traffic. Important there is that the application data, there's nowhere along the path that has access to those keys except the end device and the application server. Cool. So yeah, LoRaWAN security features briefly. We have the application keys that, I hate the naming of this, God. Application keys versus application session keys. The application keys, we're referring to the set of pre-shared keys. So before we ship a device from the factory, we put a pre-shared application key on that thing that we need to derive somehow, magic, and it should be unique to the device before we ship it. Similarly, we'll remember that application session key and we'll keep that on our join server. There's the dynamic session keys that we just talked about, the network and application key. Then we also have some other security features, like we have frame counters we have a counter for uplinks, one for downlinks. The aim there is it's a relay prevention, a relay attack prevention thingy. And we also have a join nonce that helps with the same thing. And we also have message integrity codes, which are a cryptographically robust way of making sure that the data hasn't been modified in transit. All of this, we use 128-bit keys. It's all AES, and the key derivation algorithms are very similar to the ones that are used in like Zigbee or the 802.15.4 family of protocols, the whole bunch of them. So it's pretty standard. I will mention that there are some shortcomings in LoRaWAN 1.0 that were fixed in LoRaWAN 1.1, but moving from one version to the next is a pretty big overhaul. So. But they're mainly like replay prevention or mitigation strategies that are not really a big deal for us in the field. One of my favorite features of LoRa is something called adaptive data rate. So the aim here is that the network can optimize data rates, airtime, and energy consumption dynamically. So we can modify the spreading factor and the bandwidth and the transmission power dynamically. So effectively, the device wakes up, it joins the network, and it will start with its most pessimistic radio frequency sort of settings, if you will, right? It doesn't know where it is, it doesn't know how far the gateway is, so effectively it will use like its largest transmit power and its most pessimistic spreading factors. So a real world example might be that, in order to send 10 bytes to say like I'm here and I'm healthy, a spreading factor of 10 might take 370 milliseconds of airtime, which is an eternity for little devices like this. And it might use its maximum allowed transmit power, which I think in North America is 20 dBm or 22, I can't remember, but it's like 100 milliwatts kind of thing. So if the network server realizes that transmission came in loud and clear, it can schedule a downlink to instruct the node, like, hey, dude, I heard you really loud and clear. Like your RSSI might be like, negative 50 decibels. So like, dude, you can calm down and, so you can use a more favorable spreading factor, and you can also take your transmit power way down. So the device may say, I'm going to use spreading factor 8, and I'm going to use 1 milliwatt instead of 100. That time on air then goes down to, I think, 28 milliseconds, right? So you can see how the adaptive data rate makes a huge difference in terms of the battery consumption of these end devices. It's absolutely massive. Quick note about uplinks and downlinks. So again, they're battery-powered devices, so you're probably asking if it's battery-powered. Probably means it's sleeping most of the time, so how do you downlink to a thing that's sleeping? It's kind of neat. You have two chances. So our device will wake up. It'll send an uplink or a transmission. It'll wait a fixed delay. So there's two windows of opportunity, the RX1 and the RX2 window. If the network has a message for that node, it's got to send it within those two windows of when the node is listening. So our devices then in the field, we have them wake up periodically. If it's on battery, it'll wake up 4 hours, and if it's got a reading, it'll send it to the network. Even if it doesn't have a reading to send, it'll send an uplink, which will solicit a downlink saying, do you have anything for me? If not, it goes back to sleep. Our devices that are powered by shore power or that are always powered will do that actually every 2 minutes. That's how we can send fan control messages. So you can imagine, like, you don't want to wait 4 hours to say, I want to turn that heater off, right? So, because like these are fire-breathing devices in the real world. So there's lots of keep alives. But yeah, in order to get a downlink, you have to have an uplink first. So that's a kind of a interesting, fun thing with LoRa. Yeah, my notes are messed up. Cool. Yeah, cool. So I'll talk a little bit briefly about our device implementation. We didn't write a whole LoRaWAN stack for our devices. We actually use an off-the-shelf chip from Multitech called an XDOT. It implements the entire client side, which is handy. So we essentially just use like an AT command set to talk to this thing, and we say, like, here's a payload. We're going to base 64 encode it, shove it into the XDOT, and the XDOT will be like, cool, it transmitted it, and here's a downlink, which we get in base 64. We decode, and off we go. We drive the whole thing through, I think, a SAMD21 microcontroller where all of our fancy code lives. One cool thing about that, well, the cool thing about using an off-the-shelf implementation is that we don't have to worry about stuff like FCC certifications or like making sure our crypto implementation is sound. So yeah, it's really cool. One of the problems is we've sort of baked in, like, these implement the LoRaWAN standard 102B, and so that's what we got in the field right now. And it works great. And again, like, doing FCC certifications and stuff is a pain in the ass. If we can have Multitech do it for us, that's pretty great. Let's talk about, oh cool, my notes aren't here, I love it. So let's talk about the gateway function. So the gateway, we have a couple of functional components. We have a LoRaWAN multi-channel gateway card. When I say multi-channel, LoRa can talk on a bunch of channels. Cheap gateways will just listen on one channel and say, hey, we just use channel 1, great. These gateways will implement, I think, 56 channels at a time. On board, we also have a 3G/LTE modem. Comes with a Wi-Fi access point, GPS receiver, and does router stuff, VPNs and remote access and all that kind of jazz too. We are using a cool. We are using a MikroTik LTAP, which is a weatherproof MikroTik router board. Has built-in Wi-Fi and GPS on it, which is fun. Accepts a very wide input of DC voltage, and it can be PoE powered. And most important for us, it has a crazy wide range of operating temperatures. So -40 to +70 is what it says on the tin. We've taken it to some more awful extremes than that. It has 3 SIM slots, so we can put 3 physical SIM cards in it. But most importantly, there's 2 empty mini PCIe slots that we can put goodies into. It runs Router OS. If there's any people that do MikroTik, Router OS is like a cool OS. It's esoteric and it's a pain in the ass, but it also does cool stuff for real cheap. So what more can you ask for? So these things being physically robust was really one of the big selling points. These things get caked with grain dust. Sometimes you can't tell what color they are. They get this bird shit is a massive thing. Snow and ice. The only time we've ever had one die is when it got struck by lightning. So, like literally, which is, yeah, I know we can mitigate that a bit, but it's still it's kind of a bigger problem. So yeah, we use a LoRaWAN concentrator card. We buy them specifically for either the 915 megahertz spectrum or the European 868. But we have to have our manufacturing people install them. It's actually under the PCB, so the poor people have to unbolt the thing from the metal backplate, and they hate that. And then under this thermal pad, we have an LTE6 modem. And then we bring, the LTE6 modem too has really good international band support. So, most of them are in the US right now, and we don't have full band support for the US, but we've never really had a problem getting them on the air. We're more concerned about being able to deploy these anywhere in the world and, having them just pop on the network. We've also tried a bunch of different cell cards. We've tried like Huawei and Sierra Wireless. So it's good that we have choice, but the MikroTik board, the software support's just better in Router OS for them, but we still can do like weird stuff like use AT commands with it to do like, say I want to lock you to a certain cell band or like a certain actual physical cell ID. So that's handy. You'll also see we use like these little pigtails to bring all the antennas out into the outside world. Like the Wi-Fi antennas, for example, on the circuit board, there's inverted F antennas that are right on the PCB. We bring everything out so we can use external antennas and increase our range. And all these SMA connectors will be covered by a plastic shroud to sort of keep the spiders out as best we can. Although spiders aren't really too much of a problem. This is a real ugly gateway. This is an early implementation. This isn't what our stuff looks like in the field, but I'm using this picture because you can sort of see just how all the cables come in and out. For all the RF nerds, I'll take you through the antenna array here. Top left, we have a giant LoRa antenna. This is a 6.5 dBi omnidirectional. On the right, we have a Wi-Fi, I think it's a 2.3 or 2.1 dB quarter wave omni. That's just like a DigiKey rubber ducky special. The LTE is the square guy on the bottom. That's a MikroTik MANT LTE 50, which is a 5 dBi omni. It's actually an omni, despite the fact that it looks directional. And you can't really see there's a GPS receiver, which is just sort of a patch antenna on top of the metal bracketry there. The GPS is just sort of a flush mount, but it's a powered active antenna too, because, I don't know, GPS. And you can also see the blue cable. We have PoE. Well, actually, it's not really PoE. We use Ethernet just because it's cheap and cheerful, and we just run 24 volts DC from the ground up. So whatever. And then all the installers pretty much have Ethernet and crimpers in their trucks. So we're just like, plug it in the Ethernet port. It's all good. So why don't, I've said, yeah, these are deployed in the middle of nowhere. You'd think, oh man, you probably have to use directional antennas for the LTE. Not really. If we install our gateway near the ground and have crappy cell signal, there's lots of places on these farms to just put shit higher. So, getting 100 feet off the ground is like, yeah, no problem. As long as I'm not the poor sod who has to go up and mount it on top of a grain leg. But whatevs. No, our installers go on the grain leg, not the farmer. The farmer's like, I don't care, but I'm not going out there. A quick note about the software that we put in these gateways. So from the factory, we just sort of put like a preload image on it. So basic LTE config, or like basic cell config, and sort of a call home OpenVPN type of thing, like pre-shared keys. So it just calls home to a provisioning server and waits for instructions. So yeah, after the thing's installed, we'll SSH over to the VPN. We'll say, who are you? Where are you? Are you at the same place where our installer is? And then we'll do some personalization to it. One of the problems, of course, is that when we put these things in the middle of nowhere, we don't really know which cell network it's going to be on. And there have been a few cases, both in Canada and the US, where the cell modem will register on the operator and get an IP address, but have no connectivity. If you've ever been in the middle of nowhere and your phone says like Rogers EXT, so the Rogers Extended Roaming Network or whatever, Verizon has something similar. These are the problems that we're talking about. It's like, cool, welcome to the network, but you can't move traffic because we're using this mobile virtual network operator. So we've had to do some script effery to say like, yeah, cool, you're online, but can you actually move data? If not, try T-Mobile, and then if that doesn't work, try Verizon, and then try whatever, in sort of an order of preference. So that's not always crazy fun. Cool. Okay, so when the thing calls home, we then give it a personality. We give it a custom OpenVPN certificate instead of pre-shared keys. We do some basic management with Prometheus and LibreNMS rather. We configure its LoRaWAN parameters, and we will often lock it to a cell provider. Again, like in the US, we might say AT&T is best-ish, but we'll try a bunch of different providers and say like which provider has like the lowest round trip. I don't really care about bandwidth. We're not moving a lot of data, but what's got the most stable connection with the smallest latency. So then we'll often just pin it to that carrier, say like, hey, you live on T-Mobile now, and then cool. Then we can do LoRa stuff. Just a passing thing. Why is there Wi-Fi in these things? Well, first it just comes as part of the thingy. Again, it's on board. But it's super handy for on-site techs to say like, if something's wrong with the gateway, you don't have to climb to the top of the bin or like on the drag conveyor to go service this thing. You can just be wherever you are on site. We can generally see the things for like 500 or 700 meters with these little rubber ducky Omnis. So it's kind of a big serviceability bonus that we can just say like the thing's alive, but it's not online. Go into the MikroTik app on your phone and just like make the thing do make it go whir. So that's kind of handy. Yeah, so much cell crap. Our mobile virtual network operator. So this is interesting. We have one SIM card, or one type of SIM, if you will, and it has one APN, or one network name. But using this, we can drop this into like over 200 countries. It'll work on over 400 cell providers. So it's pretty cool. But one of the downsides is that our MVNO is out of Europe. So all the devices look like they're in Sweden, which is kind of neat. But they work on carriers all over the world. So in Canada, we have Bell, Telus, and Videotron. In the US, we have AT&T, T-Mobile, Verizon, ComNet, Vario Wireless, AWN, and Union. Oh, man. And we've requested that they actually add a whole bunch of like little mom and pop or cell providers that actually still exist. They haven't been bought up yet. So yeah, once the device registers as roaming on the operator, yeah, that traffic just pops out in Sweden, which is pretty cool. You're probably asking yourself, well, why don't you just use the customer's network? Like everyone's got Wi-Fi. What the hell, man? And yeah, it sounds like a good idea until you're trying to troubleshoot a customer's network. They're like, I can't see my grain bin? And I'm like, well, your network's shit. So, then they're like, oh, I gotta call my nephew and he's my Wi-Fi guy. And like, it's crap, right? Like we've tried it. Our salespeople are like, no, they want to use their own network. And I'm like, nah, bro, that's a dumb idea. That's why we use an NVMO. Yeah, whatever. So one quick aside, cell stuff is just a disaster sometimes. Cellmapper.net is like one of my best friends. Sometimes like there'll be a tower, like you can see the thing. Like why aren't you on that tower? Cellmapper will help you figure out like which operator is where based on your GPS location, which segment you should talk to. So it really helps in optimizing. If you have stuff in the field, Cellmapper, especially in the US, can be a real asset. And again, a lot of this is black magic, but yeah, it's super helpful. So yeah, our Swedish traffic trombone, super weird. So isn't it a problem? I talked a bit about LoRaWAN and its timing, right? Like we have a fixed RX1 and RX2 window, right? The thing wakes up, waits a second, and if we don't get a downlink, that's it. That's your only opportunity. So like, is this a problem? And I thought maybe, so we tested it. We spent quite a long time testing it. And yeah, the answer is loosely, nah, it's cool. Our traffic trombone introduces an additional, let's call it 300 milliseconds of round trip time. Again, so our devices, just to be clear, our devices are in Canada and the US. The traffic magically appears on the internet in Sweden and then has to come back to an AWS region in North America. Like, that's crazy beans, right? But 1,000 milliseconds is kind of an eternity. So downlink scheduling turns out to not be a problem, which was handy. The deal with this MVNO was probably made over golf with some execs. And I was like, well, that's a terrible idea. But when we tested it, it turns out it's okay, I guess. So just to answer that question. This seems like marketing to you, but so, okay, yeah, your stuff's in the cloud, now what? This is just a quick view of sort of some customer portal stuff. You can see your temp and moisture, your CO2, your outdoor weather, your plenum conditions. Oh, I didn't mention, we have sensors inside the plenum so we can detect if the fans are on or off. So the difference in pressure between the outside stuff and the inside stuff, we can detect whether the pressure is higher in the plenum to actually say, like, we sent a fan message on, did the fan actually come on? So we measure that stuff. And this shows you, yeah, like bin inventory, fill level, et cetera, et cetera. Similarly, we have the fan control page. The cool thing here is that a producer can sort of say, like, hey, I dumped soybeans in bin 3, and I want to sell them when they're at what would be a good moisture level for, well, I don't know, 18%? I just made that up. So the system will sort of say, like, okay, based on the outside conditions, I'm going to run my fans, and in an attempt to dry this or condition it to a certain level. So, smart drying or whatever marketing calls it is actually a pretty groovy thing. And of course, graphs, because graphs. So yeah, good story, but like stuff goes sideways, right? I said LoRa is like really has good immunity to a bunch of like BS, if you will. But so here's a picture of of my laptop sitting on a drag conveyor somewhere in Minnesota. I have a software-defined radio on the left, and I have a LoRaWAN development board hanging out on the right. And what you don't see is there's like corn getting unloaded off to the side. And if you've ever been around corn getting unloaded, and there's these little red bees wings things, and they get all over. It's really nasty. And it's about to snow, so good times. In this particular case, we had really like 50-50 whether or not our LoRa was going to work, and we've never had LoRa reliability problems. So couldn't figure it out. I hopped in the car, went down to Minnesota, and I was like, what the hell with my SDR? And lo and behold, there was someone else not just using the 915 megahertz band, because that's not a big deal, but they were using LoRa, which again, they should be able to, multiple networks should be cool, but holy crap, were they really saturating the RF environment. And so I was surprised. And the farmers will have all sorts of equipment from all sorts of vendors. Shouldn't be a big deal. But yeah, this was weird. As a quick aside, LoRa is known as like a pure Aloha protocol. And so what that means is that like each node or station will, when it tries to transmit a frame, will just like wake up and go bleh, and just like assume that it's cool to talk, right? So it doesn't try to detect whether transmission channel is idle or in use. Both the XDOT in our devices and our gateways, you can enable a feature, it's just called listen before talk. So the way they're configured is that they will wake up, they'll listen for 5,000 microseconds, and then if what they hear or don't hear is below a noise floor of negative 65 dB, then they'll consider the channel clear and then transmit. So that was enough to solve our problems. We're coexisting with, like, we still don't know who else was using LoRa on that site, but just using listen before talk was enough to sort of get around that. Had that not worked, we could actually switch to a different subband. The 915 megahertz band is, at least for LoRa, is sliced into 8 subbands. So we could just use a different subband, but we need a dedicated network server to do channel coordination. So, it's a pain in the ass, but we can do it if we have to. Power, you can imagine out in the middle of often nowhere that power is a big pain in the ass. It's common for us to lose power to our fan control modules, our gateways, but our cable hubs are, even if they're hardwired, they all have a solar panel and they have a lithium iron phosphate battery on board. So we can actually keep reading cables even when power is out. We decrease the frequency that we read cables, but we'll read cables until we're out of memory. And we have just sort of like a big ass circular buffer, and we'll just keep reading cables until the internet comes back. So that's pretty handy. Yeah, internet go bye-bye. This happens a lot. So if a gateway dies or if it just has connectivity problems, the thing about LoRa, remember when I said that the keys are end-to-end? So the device node talking to the gateway isn't helpful. The gateway can't read anything. It's just a fancy media converter. So essentially, if LoRa goes away, that means that we can't control anything. So we have software both on the fan control module and on the cable hub that is smart enough to know, like, the internet went away, like the software that's controlling me on the application side. Last thing I heard from it is it wants me to dry the grain, so I'm going to keep doing that. I'm going to just keep targeting whatever moisture level. And there is a point at which it's like, I've been offline for too long, I'm just going to go into remote control mode, and then, I give up, please send an adult. But there is quite a lot of remote survivability features in there. Again, like running giant fire-breathing fans is not something we want to do willy-nilly, right? So there's quite a lot of safety precautions built into the system. If stuff goes missing, not a big deal. Like the devices, we simply mark them as stolen. We revoke their credentials, no problem. On the gateways, if a gateway goes missing, again, we have issued a specific OpenVPN X509 cert to that specific gateway. We revoke that on the server, NBD. Similarly with the SIM cards, our MVNO gives us it's an OK portal, I guess, that we can disable SIMs via an API. We can also, to a lesser degree, if a SIM gets stolen and we detect misuse, we can also, detect the misuse, but we can also, disable them. And there's really nothing else really that's sensitive. Again, most of the secret sauce is all in the cloud anyway, right? And things get cold. This is kind of a special consideration. When it goes below -21, I think, we have a special operating mode called low temperature mode. That specifically disables the charging controller for the lithium iron phosphate battery because the chemistry is such that apparently you're not supposed to charge them when it's cold, like really cold. But it also puts the hub into a very low power mode so that if it's really, really cold and the power happens to go out, that we can ride on that battery for as long as possible, so we can just keep reading cable data until it gets warmer and stuff comes back. So, cool. I think I'm out of time, so I'm gonna wrap it up there. I would like to know if there's any questions about this weird stuff that I'm talking about. You. So broadly, the question is like, how fast can we pump data through LoRa? Through our devices? We don't really need to pump it too fast. But so because LoRa is like it's kind of not a real-time protocol. It's hard. Let's say it's in the hundreds of kilobits per second. It's a complicated question to answer because of the radio frequency regulatory framework that we have to operate in. So in LoRa, the actual, let's call it good put. I hate that word, but whatever, that we can get out of LoRa is substantially less. We might be talking about like tens of kilobits a second. In North America, we can actually get, hundreds of kilobits a second. But again, our application would never, unless we had like a crap ton of cable readings that we'd stored up, then we'll just be dumping frames like crazy. And we might get 170 kilobits a second kind of thing. Yeah. How many things have we got stolen? Stolen, lost. Nothing so far, but it's just sort of, the reason I mentioned, if stuff gets stolen is to say, like, to point out the fact that, like, the credentials on the device when we pre-provision them are unique to that device. So we're not reusing credentials in the field. We're issuing device-specific X5 and 9 certs kind of thing. So that's really the reason that I wanted to point those out, is that each device is provisioned with credentials that are just for that device in the field. And if, so those credentials are essentially throwaway. So that's the reason I mentioned that. Yeah. Cool. Gentleman in the hat. Sorry, what was the last bit? Is the connection 8-bit clean? Why the base 64? Because we're talking to the xdot module through AT commands. What we actually are passing to it is like a binary structure, because the payloads, again, can be as little as 11 bytes long if we're operating at data rate 10. We got to be really frugal, like every byte matters. It doesn't transmit in base 64, just to be clear, but we just interact with the xdot over base 64 just to keep it, keep it clean. So, yeah. There are cases where we've used the customer's network. Yeah. And you know what? Sometimes it's great. Like some of these big producers, like some of the co-ops have like, they're like, yeah, just pop on our fiber optic line. It's cool. And other sites are just kind of like, yeah, like literally my nephew set up the Wi-Fi. It's kind of, and then proceed to ask us like, dude, why can't I see my cable readings? I'm like, because your network is an absolute disaster, and like, what do you want me to do about it? So, yeah, if I'm the guy who's got who the problem is escalated to fix it, I want to be able to like call up my service provider and say like, what up, instead of being like, hey, can you put your nephew on the phone? Like, yeah, it's really it's sort of customer service reliability ultimately. How do we protect the physical devices against tampering and stuff? That's a good question. Yeah, they're real high, and most people are scared. No, that's a good question. How do we prevent against tampering? So the actual LoRa devices themselves, like you really can't pass. Like I guess you could pass data through them, and you could extract some stuff out of the firmware. I guess the gateway is probably more of a vulnerability for us in terms of tampering. So like again, the SIM card, you could just pop the SIM card out and like stick it in your laptop and stuff. But we do have some tools that allow us to detect misuse. Again, that's all up to our MVNO, and we get that data via API. So you can just say like, whoa, dude, that SIM card is using like 4 gigs, and it should have used like 4 megabytes this month, right? So yeah, that's effectively it. But a lot of it's just like being remote and high. I'm not going to repeat the question because I'm not really going to answer it. You're asking me stuff about money, and I'm not qualified. Cool. All right. Thanks, everyone. And we'll talk later. Thanks to the organizers, too. Thanks a lot.